Alright, I'm gonna go ahead and get started. Doesn't look like there's too many people here this morning. That's alright. It'll still get recorded, which is good. I hope you're all doing well. Enjoying self isolation as much as I am. So to start off with, this homework is saying at the top here it's due tomorrow night at midnight, and I think I said that in the last help hours. And Dr. Nigra sent out an announcement saying that this homework was being pushed back to Friday because the test was pushed back to yesterday, Monday. And good job on that, by the way, guys. I know it was a hard one, but you got through it. So, so this homework will be due on Friday, and homework 8 is still going to be due on next Wednesday. Next Wednesday is, I want to say, the 1st. Yep, the 1st. Homework 8 should still be due April 1st. So, look like there's too many people watching, but I'll still just run through the problem and have it posted. Anyone that comes in can go ahead and ask questions, and I'll try and get around to them. Oops. Sorry about that. All right. So, starting off with problem 1, we have it's a multiple steady states problem. We want to find the steady states of the following liquid phase reaction carried out in CSTR. So, as you recall from the previous lecture, that in order to find the multiple steady states, we'll want to find the points where the energy balance and the mass balance conversions are equal to one another. So we'll have to plot the energy balance and the mass balance as a function of the of temperature. So let's start off with finding the mass balance, because that's the one we've been doing the most. So for the CSTR, the mass balance, best place to start is with the design equation. So for a CSTR, V equals FA naught times XA over minus RA. For minus RA, we are told that it is a liquid phase elementary liquid phase reaction. So minus RA is going to be equal to our reaction constant K times CA times CB. And to kind of mitigate any confusion you guys might have, especially with the nomenclature in this problem, we can see that it is a 1-to-1 reaction. But we also see that CB naught, the concentration in B, has a lower concentration than A, CA naught. So that actually makes B the limiting reactant in this case. So I'm just going to put everything in terms of B, because normally we use A to indicate the limiting reactant, but in this case the limiting reactant is B. So I'll just rewrite it all. So B is equal to FB naught times XB over minus RB. RB will equal the same thing. And then looking at the reaction rates, we want to write it in terms of conversion. So we know that CB, at the very least, can be written as CB naught times 1 minus XB. And CA, and if you remember that for a liquid phase reaction, the formula for conversion is equal to CA naught times theta I minus nu I over nu A times XA, where again A is just whatever the limiting reactant is. So in this case CA, is going to be equal to CB naught times 20 over 30, because theta I could be either Ci over Ca, or Fi over Fa, or even Yi over Ya. But we're given concentration, so we're going to use that. So we have 20 over 3 minus, and then since it's 1 to 1, that term just goes to 1, minus xb. So we have a Cb naught squared times 1 minus xb times 20 over 3 minus xb. And we're not really given too much information on FB naught, so I am actually going to go and rewrite that in terms of the volumetric flow rate and the concentration. So we can rewrite this to be, remember that FB naught is equal to CB naught times V naught. So we got CB naught times V naught times XB in the numerator over K times CB naught squared times 1 minus XB times 20 over 3 minus XB. And are we given information about the volume? Looking over this, we are. And we're given V naught as well. So we can rewrite this to be equal to CB naught. Nope, that cancels. Sorry. Come on. There we go. So we'll cancel out one of those terms. V is equal to V naught times XB over K, CB naught, times 1 minus XB times 20 over 3 minus XB. And if you recall that we are trying, on that graph, we are trying to plot the conversion as a function of temperature, the reactor temperature, we need to find what in this equation has a dependence on temperature. And the answer to that is the reaction constant K. And it's related to it in terms of the Arrhenius equation. I don't think I spelled that right, but that's okay. And for this problem, we are actually given K as a function of T. And it's this guy right here. So for that part, this is going to make our, zoom out, V is equal to V naught times XB over our function of K, which is 33 E9 times the exponential of negative 20,000 for RT times CB naught times 1 minus XB times 20 over 3 XB. And for the time being, that's how I'm going to leave the mass balance. We'll come back to it and solve it later, but we'll move on to the energy balance for now. So, energy balance. Let's just start with the whole thing. 2Q dot minus W dot S minus FA naught, or I guess XB naught. My eraser will work. XB delta HR minus FB naught sigma theta I CPI times T minus T naught. All right, so in this case, we are trying to find the steady state conversions. So because we're trying to find the steady state conversions, we will assume that turned to 0. We're assuming no shaft work. Are we given any information about a jacket or it being adiabatic? So we're given a U and an A term indicating that we do have a jacket. So we'll have to consider that in Q. Ooh, it's going slow. There we go. So for a jacket, we know that Q is equal to UA times TA minus T. I believe. Yes. So subbing in our zeros, solving for a couple things, we have 0 is equal to UA times TA minus T over FB naught minus XB delta HR minus FB naught CPI T minus T0. In general, delta HR is a function of temperature. It's equal to some delta HR of formation at some reference temperature plus delta CP times T minus T ref. However, we are just given delta HR, and we're not really given any information about a delta CP. So we are going to assume that delta CP is 0 and delta HR is not a function of temperature, so that the one we have is essentially just constant. And for the sigma theta I CPI, we are given this term is equal to CP naught, right? Right here is equal to 650. So essentially the term that we want is equal to 650, but the term that we want is this one. So basically this is equal to that 650 that we're given over CB naught, which we're also given. And everything else, for the most part, we should be given. If we don't, it can easily be solved for, except for XB. So we can actually just go and directly solve this for XB, and we'll get that XB is equal to one over delta H UA TA minus T over FB naught minus theta I CPI times T minus T naught. So in this case, we were able to directly solve for X for our energy, for our conversion and our energy balance up here in our mass balance. Since we've got 3 instances of X, that would have been much more difficult, which is why I just left it the way it is. So the next step is to essentially solve these, and or plot these, sorry. And we're going to do this in Python, because that's where I like to do it. Okay, so I've got the all of our constants put in here. All the conversions, proper conversions have been made. So let's start with the energy balance. So since we were able to directly solve for this, we can kind of use a simplified version of a function solver of a function. And it's just this lambda notation. So when you say lambda, it's going to assume it's a function, and then the next value you put is the independent variable, in our case t. So oops, that one yet. For this one, we are going to put this big long equation in there. Hopefully this is showing up. Oh, it is good. Okay, so I've got should be showing. Okay. So we've got U times A times TA minus T over FB naught minus T minus T naught times sigma theta over delta H. And that's it for the energy balance. For the mass balance, because it's, which is basically the left-hand side minus the right-hand side is equal to 0. So I've got my mass balance in terms of X and T. I've got K is equal to, and I'm just putting in what was given for K. And now we're going, remember I'm putting in the residual form, so V minus the left-hand side, which we had as V times X over K over CB naught over 1 minus X, capital X over 20 over 3 minus X, capital X. And we're going to return M. All right, now I'm going to tell it to give, I'm going to give it, define T as a lens space between 300, no, what range should he tell us to work in? Told us to work between 310 and 375. Okay, so 310 and 375, 1,000 points. So for the energy balance, in order to input something in there, so a new variable and then our energy balance of T. And that will put T in for our independent variable, and that's all we need to do for that. For the mass balance, to use fsolve, we need to start off with a guess, which we can say is 0 for the initial condition. And we'll need to make a new variable for our solution. We'll just make it an empty array that is the same length as T. And fsolve only likes to solve at 1 point at a time. So because of that, and since we have a lot of points, we'll need to have it cycle through about 1,000 times. So we'll need a for loop to do this. So for I in range of 0 to length of T, the mass balance solution of I is equal to fsolve, and then fsolve, your first input is your function, second input is what you're solving for, a guess for whatever you're solving for, so in that case, x guess, and then since we have a second input, we have to do this little args thing. Make sure I get the nomenclature right. It basically tells it that this other input is a known variable, and this is what I want it to be. And then we're going to reset the guess. So we've got our mass balance to our basically our previous number, that our last answer will be the next guess. All right. And if I did this right, it should plot. So let's see. So we're going to plot the energy balance as a function of time. Let me make sure I get the labels on this. gosh, what was I doing? There we go. Solution label. And so I can make it look nice. No, I don't need to do that. Let's do a legend. Okay. Home no truth. Oh, good. Actually solved for the mass balance differently this time, and it still worked out. Perfect. So, as you can see, there are 3 locations where the energy balance and the mass balance intersect. So we got one down here, one in the middle, and one up here. So, the rest of this problem is asking that you go and find the temperature and conversion at these points. And I didn't show you guys last time how to do it. I don't know, for anyone that might be struggling to find these points, here is how I did it, basically. So you can use polyfit, which will create a polynomial kind of a polynomial line of fit to a string of data that you have. So in this case, it takes 3 inputs: your x values, your y values, and the order of your polynomial. So in this case, x is going to be t, and y in this case will be the difference between our 2 functions, because we know that if we were just to subtract these our two arrays for the energy and mass balance conversions, that we should have 3 locations where it goes to 0. And those are the locations that we care about. And since we got 3, then we'll do it as a 3rd order polynomial. And then our steady states is equal to the roots of that polyfit that we just found. So if we TSS, oops, oh yeah, I'm using old nomenclature. Let's try that. There we go. So now I've got 3 temperatures, and these are the temperatures that my conversions, that these steady state conversions are occurring at. And if you go and basically, so let's say we need to find the conversion. So let's say that the temperature, how can I do this? And it doesn't matter really what energy balance you pick. So let's say that x3, this guy up here toward the top, is equal to the energy balance at TSS of 2. The third, or no, 1, sorry, 0, that's it. So basically I'm plugging in the first temperature of this TSS, or my steady state temperatures. So when I plug in that first value into the energy balance one, I'll get a conversion, and that conversion should be the same as the one at the mass balance. So if we print x3, there we go. So that is the conversion at that location. And that's kind of that is an easy way of finding the temperatures and conversions at the points on the graph. And that pretty much covers part A. For part B, are there unstable steady state values? If so, which ones? So going back to, no, not that one. This will scroll, there we go. To this guy here. A steady state is unstable if, when you slightly increase the temperature from steady state, if the heat generated is greater than the heat removed, then that is an unstable steady state, because you're creating more heat than you can remove, and that could cause damage to your reactor and potentially result in a runaway reaction. All things you do not want. Why is this not plugged in? There we go. So, and then looking at these graphs, you can see that the heat removed is generally a linear function of T. So if we go back to this graph, we can see that we do have a linear, our energy balance is linear, so that is going to represent our heat removed. So if we pick a steady state, let's go with the one on the bottom there. If we slightly increase the temperature, that'll put us, let's just say that puts us at 320. We can see that our linear line, or the heat removed, is greater than the heat generated line, indicating that that is a stable steady state, because we're removing more heat than we're generating, and we're able to maintain the temperature of the reactor. If we look at this one, this middle point here, if we go a little bit higher, we can see that the more polynomial line, or this other line here, the heat generated is greater than our linear line, which is the heat removed. And because of that, we're creating more heat than we're able to remove, indicating that that is an unstable steady state. And then I'll have you guys determine that one. But that just about covers number 1. Give me a sec. All right, and moving on to number 2. So we have the elementary liquid phase reaction. A goes to B occurs in ejected CSTR. Species A and inert I are fed to the reactor in equimolar amounts. The molar flow rate of A is 80 moles per minute. And then we're given all that information. What is the reactor temperature at a feed temperature of 450 Kelvin? All right. So once again, we're kind of dealing with another steady state problem. So the best place to start with this is either the energy balance or the mass balance. And I like to start with the mass balance. It just makes sense. All right. So we have a CSTR. So we have that V is equal to FA naught times XA over minus RA. And we're told that it is an elementary and liquid phase reaction, so we know that minus RA is equal to K, try and write better, K times CA. And again, liquid phase, and writing in terms of conversion, we have CA is equal to CA naught times 1 minus XA. And let's see what information we're given about the inlet. So we are given this 80 moles per minute, which is FA naught. It doesn't look like we're given any information about V naught or CA naught, and it doesn't even look like we're given information about the volume, the reactor volume. But we are given information about tau. So going back over here, so we'll want to rewrite this CA naught in terms of at least one variable that we know. So in this case, we know that CA naught is equal to FA naught over V naught. And we do know what FA naught is. So we got V is equal to FA naught times, if you'll remember, tau is equal to V over V naught, volume over the inlet volumetric flow rate. So we can rewrite that to say V is equal to tau times V naught. And knowing that, we can rewrite our design equation to be tau times V naught is equal to XA V naught K times 1 minus XA. we can cancel out the V naughts, and we get tau is equal to XA over, K times 1 minus XA. And for the time being, we will leave that the way it is and move on to our energy balance. So our energy balance, starting off with the entire energy balance, is W dot minus delta HR, FA naught, the I CPI, T minus T naught. So again, we're looking at steady state. We can assume no shaft work, and I believe it said that this was a jacketed reactor. And if it's jacketed, we know that Q dot is equal to UA times TA minus T. So same as before, rearranging, you have UA times TA minus T over FA naught minus XA delta HR minus sigma theta I. Last problem, we are given delta HR at a, we're not given it really at a reference temperature. We're not really told anything about the delta CP. Actually, we can find delta CP, but since CPA and CPB are equal to each other, delta CP is equal to 0. So delta HR is independent of temperature. For the sigma theta I CPI, we'll have to consider all of them, theta B, CPB, and remember that in this problem we were told that we had an inert coming in as well. Let's do that, capital I. And it said that A and inert were initially fed to the reactor, so that makes theta B 0. Theta A is always 1, and A and inert I were fed at equimolar concentrations, so that will also make theta I 1. And let me just point it out, yep, fed in equimolar amounts. So that is basically going to be equal to CPA plus CPI. And I'm just going to plug in numbers here. CPA is 20, CPI is 30. That's going to be equal to 50. Let me make sure I get the units right on that. 50 calories per mole degree C. All right, so now we can go ahead and solve for our conversion in the energy balance. So we have XA is equal to 1 over delta HR times UA TA minus T times FA naught minus, and then we got the 50 calories per mole degree C times T minus T naught. All right, so now we have an expression for the energy balance and for the mass balance. And if you'll remember that we are trying to find the load, there we go, the reactor temperature, so we're trying to find T at T naught. So we know T naught, we don't know T. And in order to get T, we kind of have to find the conversion as well, because they go hand in hand with one another. And at steady state, the XA of the energy balance needs to be equal to the XA of the mass balance. So, keeping that in mind, we can take this function that we just solved for, and we can plug it into, we're going to plug into the mass balance, into this guy here. XA times K times 1 minus XA. And we'll want to solve for T such that minus XA over 1 times K, such that we get this to be true. And I actually forgot something on the mass balance. So going back up, what term we have to consider terms on here that are functions of temperature, and the only one that's going to be a function of temperature is going to be K. And for this, in this case, we are not just given a nice Arrhenius equation like in the last one, but we are given K at a reference temperature right here. And our reference temperature is 350 Kelvin. So we can say that K at 350 times the exponential of EA over R times, let me make sure I get this straight because I always forget. Should be 1 over 350 minus 1 over T. Yeah, it should be that. Actually, I'm just gonna steal it. There we go. All right. So now we've got an expression from our mass balance. We got an expression from our energy balance. We have an expression for K. And now we need to solve for T such that this becomes true. So going into, and I highly recommend doing this problem in Excel. And you'll see why in a sec. So I kind of already had it set up, so let me just reset it. Hopefully that doesn't break it. Okay, so up here I've got all of our constants. And I don't think there was too significant of units change in this problem. So right here, I have our expression for the mass balance. Or no, I'm sorry, the energy balance, the conversion of the energy balance. So here, I can go and put it in to show you. Let me just get rid of everything. So we know that it is equal to UA over R. No, not R. FA not. Times TA minus T. Minus, should I get this in, our theta term times T minus T naught over delta H. All right, and K. K, again, is just the Arrhenius equation, so I've got my K at 350 times the exponential of EA over R times, oops, there we go, come on, 1 over 350 minus 1 over T. And then the mass is equal to tau minus my conversion over K times 1 minus the conversion. I messed up somewhere. Oh, that's why. I can't do it. There we go. All right, so if I did all this right, and I hope I did, and I'm going to use goal-seek, if I can find it, to do this. We want this cell, which is the mass balance, to be equal to 0 by changing our temperature. And hopefully this worked. It didn't, and it could be because I guessed too low. So let's try a little higher. Unfortunately, with this problem, if your guess isn't basically the answer, it's going to be very difficult. So same thing, equal to 0 by changing temperature. And that time I got it. So that's our answer for part A. 399, almost 400 degrees. All right, and for part B, plot the reactor temperature as a function of the feed temperature. So essentially, A is just, part B is, we're repeating part A just at a range of temperatures. And this is what I set up in the last help hours, and I really don't feel like going back through it again, because this is not a fun problem. So what we are expecting to get out of this problem is going to be something similar to it's going to essentially be an ignition extinction curve. Something like this. Where we are going to be following this this lower steady state branch up to a certain point, and then all of a sudden it's just going to increase. We're not going to be able to follow this lower branch anymore, and we're just going to shoot up to this upper branch where that will increase. But that one can also decrease a little before it just shoots back down to this lower branch. And you're going to find that your graph is going to look very similar to that. And because of this region here where you've actually got 2 and even 3 solutions, you're not going to be able to, it's going to be very, very difficult to do this in Python. So, looking at how I have it set up here, ignoring these big empty blocks that say part E, D, and C, a good range of temperatures to assume would just be 300 to 450, and incrementing up by 25, that's perfectly fine for part B. So in this line here, this line is basically exactly what I had right over here on the left side. So I am solving to make this mass balance equal to 0, and it's pretty close, by basically changing the temperature. And it's got the conversion and K, all as a function of T. And then I'll get rid of these just so it's a little less busy. And then once again, 325, increasing the temperature. I'm solving to set the mass balance equal to 0 by changing T, which is also going to change my conversion and K. and I'll leave these other points for you guys. But you're eventually going to reach a point, and I kind of highlighted it here in this 375, where you're going to have two separate. You're going to have two solutions based off of whatever guess you pick. So in this case, if you pick a lower guess, and I can reset these just to show you. So let's pick 320 and 370. So depending on what you pick, and again, so to kind of clear things up, so this temperature goes to this conversion, and it goes to this K, this lower K, and to this mass balance. This upper temperature goes to the upper conversion, K, and mass balance. But overall, it's the same function in there. So they've got the same function, but they've got different solutions. So we're going to set this one to 0 by changing this guy. And there's our solution for that one, and then we can do it over here to do the same thing. Set that one to 0 by changing him. And we get 372. Good. So as you can see, we have two solutions. And when you go to plot these, you're going to kind of see that it's going to look pretty linear up until, and for both of these, a certain point. So as this one increases, it's just going to keep looking linear, linear, linear. Then all of a sudden, you're going to get to a point where you can't solve it anymore. And that's the point where we have ignition, where all of a sudden we've jumped up to this point. And then with this guy, he's going to keep increasing. He's just going to keep going. But he's going to be decreasing linearly, essentially, until you get to a point where you cannot solve it anymore. And that would be your point of extinction, sorry, not ignition. Extinction, where we're just going to drop back down to this curve. And in the last help hours, I did not realize this because I was kind of following on my homework from last year. But I told you guys to use a guess of 355. So let's go and solve that just to show you that it can solve. So we're going to set that one to 0 by changing this. And it's solved. So there's our mass balance went to 0, and we have a temperature. However, this isn't a stable, steady state, because if you'll go back to this graph, you'll see that your lower branch and your upper branch should remain basically linear the whole way through. But if you see here that if I'm considering that point, I'm not linear anymore, it stopped being linear. And that's because that I accidentally went, and I didn't realize this, but I accidentally went and solved for one of these unstable steady states. And for this problem, we're asking that you look at the stable steady states. So what's on these linear lines here. And for the most part, your graph should look linear. So if you go back and watch the other video, you'll see that I chose that number. And I did that on my homework from last year, and I'm realizing now that that is actually an unstable steady state, and it's not going to be technically on our upper or lower branches for the ignition extinction curve. So at least for that one, 372 is how you want to go. So, and then again, 450, you guys don't really need to go higher than that, and you already solved for 450 over here, and then work your way down. And as I said, if you can find the values for these temperatures on the left side here, that would be sufficient for part B. All right, and for part C, so suppose you begin with a feed temperature of 250 Kelvin, which you slowly increase. What inlet temperature must the reactor be heated before the reactor operates at a high conversion? What are the corresponding temperature and conversion of the fluid in the CSTR just above this inlet temperature? So looking at our graph, so it's asking that we start at 250, which I didn't plot that far, but we don't need to for this one. So you can see it's looking pretty linear. So if we start at 250 and we just increase, we're just increasing it. And as I mentioned before, on an ignition extinction curve, you're eventually just going to reach a point where it's just going to shoot up. And when when it shoots up, that's ignition. And when it all of a sudden ignites, you're all of a sudden going to have a lot better conversion. Operates at a high conversion. Because if you look at the conversions we have for this lower branch, and these two here, these ones solved, and that one too. So we're looking at like 0.8, a conversion of 0.8%. But up here, on this upper branch, if you look at these two values, we're seeing a conversion of 99.8, 99.6, and even at 375, like 50 degrees lower, we're still operating at 95% conversion, as opposed to at the same inlet temperature for the on the lower branch, like less than 1%. So all of a sudden, when we jump up to this upper branch, essentially, is when we are going to be operating at a high conversion. And what this problem is asking for, basically, is what is the inlet temperature that ignition is going to occur at. Essentially, at what point will this lower branch stop existing? Will no longer offer viable solutions. And when the second part of that problem asks, what are the corresponding temperatures and corresponding temperature and conversion of the fluid in the CSTR just above this inlet temperature? Well, we know that once we hit ignition, we're going to all of a sudden jump up to this upper curve. It is essentially asking, when you are on this upper curve, what is the temperature and conversion? And that's kind of what these boxes are showing here. I was kind of trying to give you guys hints that ignition is going to occur somewhere between an inlet temperature of 400 and 425 degrees C. All right. And that one, it's going to be a little tedious, but it's going to take a lot of guessing and checking in order to solve for it. And the best way to go about it is to, again, ignition is going to occur. The ignition temperature is going to be essentially the last temperature that you'll be able to solve the lower, that you'll be able to find a solution for this lower branch. So, not a terrible way to start would be basically to start at 400 and just work your way up to 425. And eventually you'll get to a point where you can no longer solve, and then that helps narrow the window for you to actually find the solution. All right. For part D, suppose the inlet fluid is now heated 5 degrees above the temperature in part C and is cooled by 20 degrees C where it remains. What will be the conversion? So as I mentioned, in part C, you're essentially looking for the ignition temperature. Let's just pretend like this is our graph. So you found the ignition temperature. Now it said the inlet fluid is heated 5 degrees. So if we're going to heat 5 degrees, we know we can't increase 5 degrees on this lower branch. We have to jump up to here, up to our upper steady state, upper branch steady state. So we increase a little bit. So essentially that increasing is just saying that we are now for sure on this upper branch. And then it says that we decrease our inlet by 20 degrees C. And when we decrease, we have to stay on this line. The only way we can drop back down to this line is if we go to the extinction temperature. But it does not explicitly say that. It just says that we've decreased 20 degrees C. So we have gotten to this point, we increased a little bit, which causes us to go to the upper branch, and now we're going to decrease by about 20 degrees to around there. And it's asking for the temperature and conversion at that temperature, or at that inlet temperature. So again, that's going to take more guessing and checking, and I tried to give you guys a hint on that one. That one is going to be between 375 and 400. And you'll really only care about the upper branch for this problem. Because as I said, because of the nature of ignition extinctors, you're going to remain on the upper branch. All right, and part E. What is the feed temperature which will cause extinction for this reaction? So this one explicitly says that what is the extinction temperature. So extinction is going to occur basically at the lowest possible temperature that you can find a solution for the upper branch. So going back to the graph, I kind of gave you guys a hint on that one. On part E, it's going to start at 375. It's going to be between 350 and 375. And when a good way to start with this one is kind of the same way you did part C, is start at 375 and start solving for the upper branch and trying to get a solution and just working your way down. And once you get to a point where you can no longer find a solution, that's a good indicator that that inlet, whatever that inlet temperature you found, that is the solution. All right. And then moving on to part 3, or number 3. Okay, so in my opinion, this one is the easiest one because this one you can all do by hand. So this one, propylene oxidation to acetone, is believed to proceed via the following elementary steps, and this is a catalyzed reaction. So find the overall rate expression if step 1 is QE. Okay, so this goes back to rate mechanisms that we so fondly remember. So overall, the way I started this problem was understanding what the oxidation of propylene was to acetone. So propylene is this C3H6, and we oxidize it, oxygen, and we make acetone. Oops. Oh, now we need to balance this guy, and when we balance it, we're essentially just going to get, make sure I have it correct. We will have 2C3H6 plus O2 goes to 2C3H6. Oh, and that's the reaction, the overall reaction at least. So knowing that, we will have, and here is our rate. So this is the overall, and our rate 2S goes to, make sure I get this, there we go. We have C3H6 OS H6OS and C3H6OS goes to H6O and S. All right, so we got step 1, step 2, step 3. And these two are reversible. So we will have to consider what the stoichiometric numbers for these reactions are, these thetas. So looking at our steps and our overall, we see we need to have 2 instances of propylene, the C3H6, and we only have that occurring in one of our rate reactions, step 2. So we know that step 2 needs to be have a stoichiometric number of 2. For number 3, it's kind of the same concept. We see we need to have 2 instances of acetone, and we only have one equation actually giving us acetone step 3, so that one's also going to be equal to 2. And then the last one, we need to have one O2, and we have one equation with O2, and it only has one, so we can set that equal to 1. And then, going forward, we want to find the overall rate, R, and we know that based off of our rules on knowing what the rate determining step is, the rate determining step will be irreversible as long as there's an irreversible step in the mechanism. So unless all the steps are reversible, the rate determining step will always be irreversible. And in this case, we only have one irreversible step, and that is step 3. So we can, and if you remember that R is equal to Ri over sigma I, so it's equal to R3 over 2. And we can rewrite that to be in terms of our what we have. So we have K3 over 2, times the concentration of the species. And in doing these rate expressions, we know that we cannot leave any of our catalyst terms in the final rate expression. So we cannot leave, so we can have no S or the surface species in the final rate expression. Because while catalysts do assist in the reaction, they are not actually part of the reaction, so we don't want to have them at our reaction rate. So we need to find a way to get rid of this term. And the assumption we've made for this for part A is that the step 1 is QE. So if step 1 is QE, we can say that K1 times the concentration of O2 times the concentration squared of the S is equal to K minus 1 times the concentration of OS squared. Make sure I did that right. Yes, I did. Okay. And if you'll also kind of remember from the slides, depending on the power of the surface species, in this case, it's to the power of 2, we have to divide by the CT, or the total number of sites. It kind of helps maintain a probability. And to kind of help remember that if we have a surface species cubed, we have to divide it by CT squared. If we have a surface species, any surface species to the power of 4, we have to divide it by ACT cubed. In this case, for the overall rate, it was just to the power of 1, so we didn't need 1 at all. So, but in this case, our CTs will cancel. And for this, let's solve for the surface species, which is kind of like our reaction intermediates. So we'll end up with K1 times O2 times S. And that was just solving straight for the surface, the oxygen surface species. All right, so moving on. We still haven't solved for C3H6O.S, but we can do a pseudo-steady state analysis, make a pseudo-steady state assumption on that. So that will basically equal to the rate of that, overall rate of that is going to be equal to 0. It's going to be equal to the creation of it, which is K2 times C3H6 times O.S, and then the consumption of it. So it's consumed in the reverse step, and it is consumed in reaction 3. Or step 3, not necessarily reaction 3. Solving for it, S, going to end up with K2 C3H6 times O.S over K2 plus K3. It's not K2, it's K minus 2. And we know our expression for O.S. We just solved for that. S times over, oh my god, plus K3. So we plugging that back in to R, we have K3 over, so we have K2 times K3 times C3H6 times S times K1 times O2 over 2 times K minus 2 plus K3. And are we done? Well, going back to what we said up here, we said that we can't have any catalyst or surface species in the final reaction, because while the catalyst does help the reaction, it's not actually part of the reaction. So we can't have any S terms or OS or the C3H6OS terms. Do we have any of those terms here? Yep, we have an S term. We can't have that. So in order to get rid of that, we will do a site balance. So we'll say that CT is equal to, and a site balance comprises of all of the surface and catalyst species. So we've got S, we've got the OS, and we have the C3H6OS. So that represents all occupied and unoccupied catalyst species. And we do have expressions for each one of these, so we will leave S the way it is, because that's ultimately what we're trying to solve for. We know our expression for the C3H6, or let's do the OS first. And then we know our expression for C3H6OS. That was this guy right here, who I'm just going to gratuitously copy. I tried my best. All right, so now we can take a concentration of S out of each one of these and solve for it. We will get that concentration of S is equal to CT over 1 plus K1, 2 plus K2 over K minus 2 plus K3. And then, yes, I know it's messy, but there's our expression for S. And while we can't leave S or any of the surface species in our final rate expression, we can leave CT in, because CT is kind of like a constant. So, all right, how do I want to do this? All right, so we've got R is equal to K2 times K3 times C2, 3, not 2, H6, K1, O2, over 2 times K minus 2 plus K3 times this term. And there you go. That is part A. So, very hand cramping, but I think it's not too terrible. It is, if you remember mechanisms decently well, then this shouldn't be too difficult for you guys. And if you do struggle a little bit with mechanisms, this will be a great practice. If you need a little bit of help, especially with this beginning part, I recommend going back to the older homeworks and maybe even mini-term 2 for some refresher. Okay, so that was part A. Moving on to part B. All right, find the overall rate expression if step 1 and step 2 are QE. Okay, so last time we only assumed step 1 was QE, and when we made that assumption, we also said that the concentration of OS is equal to this. This will remain true because assuming QE on step 2 isn't going to change the nature of, isn't going to change step 1, and we can still assume QE on step 1, so that is still true. So the big difference is QE on step 2, and when we assume QE on step 2, we can say that G3H6O, nope, not O, 2K minus 2, oh my gosh. O dot S. There we go. This is our QE assumption on step 2. So, solving for what we don't know yet, we can say C3H6OS is equal to capital K2 times C3H6 times OS, which is equal to, oh my god, my handwriting deteriorates the more I do these mechanisms, I'm sorry. Trying my best. See, oh, my sanity too, good lord. Right there. So that's just plugging in our expression for OS that we solved for in part A. So we're trying to find the overall rate expression still. R is equal to R3 over 2. That remains true. And now we can plug in. So we have, and well, this still remains true as well, based off of step 3. So we can say K3 times K2 times C3H6 times S times square root of K1 O2 over 2. All right, all good. Are we done? No, we're not. Same problem is in part A. We have that concentration of S term we need to get rid of. We can do it the same way, where we do a site balance. Concentration of S plus O dot S plus concentration of her C3H6O dot S. So plugging that in. Plus, and this expression up here, because I've decided to be lazy. All right, and same as before, solving for S, we can say that CT 1 plus capital K1 of O2 plus capital K2 6 times K1 O2. There's our expression for S. Now plugging that back into the overall rate, so we have R is equal to K3 times capital K2 times the concentration of propylene times the square root of K1 O2 over 2 times this guy here. I don't feel like rewriting. And let me just check to make sure I did that right. I think I did. I did. Great. Perfect. Yeah, that's your expression for part B. And there really isn't a way of simplifying that. Sorry. That's just, that's what you end up with. All right, so for part C, here we go. Write the apparent rate constant, K apparent, and the apparent activation energy, E apparent, for the mechanism in part B if O.S is the massey. So we're going to be not necessarily using our answer in part B, but using the work in part B. So essentially what it's saying in part B is that QE for steps 1 and 2 are still valid, and the expressions we found as a result of that are still valid as well. But we have now made the assumption that CT, so remember we said that CT is the site balance for all empty and occupied surface species. We have said that OS is massey, and that essentially says that the concentration of OS is so much greater in comparison to the other ones, in comparison to S and the acetone, that they essentially go to 0. So we can say that CT is equal to O.S, which greatly simplifies our expression for, which will greatly simplify our expression for S, because remember, we still have S is equal to, O.S times square root of K1 times O2. That is still true. But now you can see that our expression for S is much smaller. Ugh. Oop, that's wrong. All right, so going back to the original rate equation, where are we going to? Right here. We're going right here. So we can take that and we can say, because now we have a new expression for S, but our expression for the acetone surface species was still true. We can say that we have K3 times K2 over 2, well, let's not do that yet, times the propylene times the square root of K1 O2, make sure I'm writing this right, times our concentrate, and then times CT over 2 times square root of K1 O2. There we go. And in this case, we do have terms we can simplify, so that term will go to 0, or cancel out, not go to 0. And we'll end up with over 2. That was not good. That's not good either. All right, there. That is acceptable. So that is what our new rate expression looks like. And our apparent activation, no, not activation, our apparent rate constant, K apparent, is essentially the culmination of our constants. That term right there. So our activation energy, or I don't know why I keep saying that. Our apparent rate constant is this. And to find the apparent activation energy, this kind of goes back to the that graph of log of k, or log of k apparent in our case, versus 1 over t. And if you remember, those graphs are usually negative, and the slope of that graph is equal to EA, the apparent activation energy, over R. So the derivative of K apparent over 1 over T is going to be equal, and it's kind of just going to be, no, it's not, sorry, not K apparent, it's log of K apparent. And if we take the log of this side, we have to take the log of this side. And when we take the log of that side, it's going to turn into, we can apply that summation, the rule of logs, where log of K apparent will be equal to log of K3 plus log of K2 plus, no, minus log of 2. And we take the derivative of these terms. 2 is a constant. It's going to go to 0. So we will have d log of k3 over d times 1 over t plus d, oh Lord, log of capital K2 t. All right, and for the, as we said before, that the slope of K apparent in 1 over T is the activation energy, or I guess the negative activation energy, because remember it's a negative slope. So this guy is going to turn into negative E3 over R. For the reversible step for capital K2, let me rewrite that so it's not so ugly. I guess that's better. It's not the activation energy, it's instead the heat of reaction, because if you'll remember kind of the Van't Hoff equation, when we use the Van't Hoff equation to find K at a different temperature, we don't use an activation energy, we use delta H. So that's going to be, also, but it follows basically the same. Delta H of 2 over R, and then that's going to be equal to negative E apparent over R. So all our negatives will cancel, and our R's will also cancel. So we have E apparent is equal to E3 plus delta H2. And for step 2, let me take a look. I can find the assignment. There it is. For step 2, that is where the actual reaction is taking place. And since oxidation is generally an exothermic reaction that releases energy, we can say that delta H2 is less than 0. And because of that, we can say that E apparent is going to be less than E3. And ultimately, for part C, that is what we are looking for. All right, so that basically covered the whole assignment. Good job, everyone. So, doesn't seem like there's many people online right now. I'll stick around for a few more minutes and answer any questions people might have. If I don't get any, I'll just end the stream early. I'll still have this one posted. I'd also remind you that Katie is still going to have help hours later today, and Dr. Niger as well. I think I went and looked. Dr. Niger has help hours from 1 to 2, Monday, Tuesday, Wednesday. And I want to say Katie's are at 2. I guess maybe I should look here. I want to say Katie's are at 2, and we'll go to 4. So any other questions, if you guys have questions there, and thinking back, I think Katie said that she will also have office hours on Wednesday from 4 to 5:30. And I know this homework is due Friday, but there's a lot of opportunity to get it done by Wednesday. So I'd encourage you to get it done by then, because even though this is due Friday, for Friday help hours, I plan on just covering homework 8, and I think that's what a lot of people are going to be expecting as well. So I know it's been a hectic weeks plural, I guess, but I would encourage you to still get it done by then. So if there are any questions, feel free to ask. If I don't get any in a few minutes, I will just end the stream early. So ask away, and if not, then I will see you guys on Friday, and I wish you luck.